Chiral objects are objects that are not superimposable on their mirror images. The word chiral comes from the Greek word for hand. So your hands are examples of chiral objects. So we have our left hand, and if we reflect our left hand in a mirror, we obviously would get our right hand. And if you try to superimpose your right hand on your left hand, you will not get it to work. The best way to think about this is a baseball glove that fits your right hand. If you take that baseball glove off your right hand and put it on your left hand, you'll see that it will not fit. So mirror images that are not superimposable on each other are called chiral objects. So therefore, these two hands are isomers of each other, because the word isomer means same parts. So we saw that in our earlier video. So isomer means same parts. Hands are obviously composed of fingers, a thumb, and a palm. So they have the same parts, but it's how those parts differ in 3 dimensions that makes them different molecules or different objects. So we actually call these stereoisomers, with the word stereo referring to the difference in 3 dimensions. So your hands are stereoisomers of each other. Let's apply this concept of chirality to an actual molecule. So let's go ahead and draw a picture of a molecule, and let's put carbon attached to fluorine, attached to a hydrogen, attached to a bromine coming out at us in space, and then a chlorine going away from us in space. So I need to draw the mirror image for this molecule. So the way I do that is to draw these little dashed lines so I know approximately where those atoms will be, and then I draw my mirror and I reflect the molecule in the left in the mirror, and I'm just going to draw what I would get. I would draw what I would see. So I would get a hydrogen here, a carbon here, my chlorine is going away from me, my bromine is coming out at me, and my fluorine is going down like that. So I have 2 molecules that are mirror images of each other. And if I took the molecule on the right, I would not be able to superimpose it on the molecule on the left. So if you have a molecular model set, go ahead and take it out, make these 2 molecules, and then take the molecule on the right and say, how can I try to get the molecule on the right to look like the molecule on the left? Well, one way to do it would be to take the bromine and then to rotate it over here to try to get the bromine on the left position and coming out at you. And when you do that, you will see that the other atoms don't line up properly. And no matter what you do, you will not be able to get the mirror image to be superimposable with the molecule on the left. Therefore, they are different molecules. They are stereoisomers. And you know that stereoisomers will be present when you have a chirality center. So a chirality center is an sp3 hybridized carbon, which therefore has a tetrahedral arrangement around it, and it must have 4 different groups attached to it. So 4 different groups. So there's a bromine here, there's a chlorine, there's a hydrogen, and there's a fluorine. So anytime you have an sp3 hybridized carbon with 4 different groups attached to it, you can say that that carbon is a chirality center. So we'll go ahead and identify that carbon as being a chirality center. There are several different terms that you will hear used instead of chirality center. There's chiral center, there's stereogenic center, there's asymmetric center. All of those terms mean the exact same thing. Chirality center is the term that's most preferred these days. So these 2 molecules are different molecules. They are stereoisomers of each other. They are made up of the same parts, but they differ in 3 dimensions. And there are specific types of stereoisomers called enantiomers. So these are stereoisomers that are non-superimposable mirror images of each other, and it comes from the Greek word for opposite. Let's take a look at a molecule that is achiral, so a molecule that does not have a chirality center. So, and objects that are superimposable on their mirror images are said to be achiral. So if we had a carbon here bonded to 2 fluorines like that, and then we had a hydrogen coming out at us, and then we had another hydrogen going away from us, and if we reflected this molecule in a mirror, we would obviously get the mirror image. So let's go ahead and draw our mirror. Something like that. And we know that my fluorine is going to go here It's bonded to a carbon, hydrogen going away from me, hydrogen coming out at me, and a fluorine going down like that. So once again, take your molecular model set, make these two molecules, and try to make the molecule on the right look like the molecule on the left. So once again, one way to do it would be to take this hydrogen and rotate this hydrogen over to this position so the hydrogen is on the left and coming out at you. And you will see that you will be able to superimpose the molecule on the right on the molecule on the left. So it turns out that these are the exact same molecules. This is not a chirality center. These are not stereoisomers. These two pictures represent the exact same molecule. So this molecule is said to be achiral. And you could have figured that out by looking at this carbon and noticing that this carbon does not have 4 different groups attached to it. The fluorines are the same, and obviously the hydrogens are the same. So that's the fast way of figuring out how many chirality centers you have. Look for sp3 hybridized carbons, look for 4 different groups. This molecule does not have it, therefore it is achiral. Let's do some examples where we're trying to identify how many chirality centers are present in our molecule. So let's start with this molecule right here, and let's put an OH group on it, and then a hydrogen going away from us in space. So let's look at each carbon individually here. Let's start with this carbon right here. Well, this carbon has 3 hydrogens attached to it, so it could not possibly be a chirality center. These 2 carbons over here on the right have at least 2 hydrogens attached to it. The one down here has 2 hydrogens attached to it. The one up here on the right has 3 hydrogens attached to it. So even though those are sp3 hybridized, they could not be chirality centers. When we look at the carbon with the OH attached to it, it's an sp3 hybridized carbon. And let's see what kinds of groups are attached to it. Well, there's an OH group attached to it, an H group attached to it, a methyl group attached to it, and an ethyl group attached to it. So that's 4 different groups. So this must be a chirality center. So this carbon right here is a chiral center. And so there's 1 for this molecule. Let's look at another molecule. So something like this. So we still have an OH there. We have a hydrogen going away from us. Let's look at our carbons. Well, this carbon right here, it's sp3 hybridized, but once again it has 3 hydrogens attached to it. So no. This carbon has 2 hydrogens attached to it. So no. This has 2, this has 3. So none of those are chirality centers. What about this carbon? Well, let's look at the groups attached to it. There's an OH attached to it, there's a hydrogen attached to it, there's an ethyl group attached to it, and there's another ethyl group attached to it. So those ethyl groups are the same, so there are not 4 different groups attached to it. So there are 0 chirality centers in this molecule. Let's do another one. Let's look at something that has a carbonyl in it. So let's do an OH group here for a carboxylic acid, and let's put a chlorine over here, a methyl group, and a hydrogen. So how many chirality centers are there in this molecule? We'll start with this carbon right here. Well, immediately you know this carbon could not be a chirality center because it is sp2 hybridized. So that carbon doesn't work. Let's look at this carbon. Well, it is sp3 hybridized, so it's tetrahedral arrangement of atoms around it. There's a chlorine attached to it, a methyl group, a hydrogen, and then we have this carboxylic acid group attached to it. So there are four different groups attached to this carbon. So this is a chirality center. Let's do one more example. Let's do this one right here. So let's use a benzene ring, and let's attach something to our benzene ring. Let's put an OH group here, and let's put an NH here with a methyl group. So how many chirality centers are there in this molecule? Well, let's start with all of the carbons on my benzene ring. Well, they're all sp2 hybridized. Therefore, they could not possibly be stereogenic centers or chirality centers. What about this carbon right here? 3 hydrogens attached to it, so that doesn't work. Same with this carbon, 3 hydrogens attached to it, so that doesn't work. And if I look at this carbon right here, the one with the OH group attached to it, well, there's an OH group attached to it. There's all this stuff here on the right. There's a a phenyl group over here on the left, and then there's also a hydrogen attached to it. So there are 4 different things attached to this carbon, so this is a chirality center. What about this carbon right here? There is an amine attached to it, there is a methyl group attached to it, there is all of this stuff over here on the left, and then there's also a hydrogen, so this is also a chirality center. So it's possible to have more than one chirality center in a molecule. Let's do an example of a ring system. So how do I identify chirality centers in a ring system? Well, if I had a cyclohexane ring, and then I put a methyl group right here, and then a hydrogen going away from me. Well, if I think about where are my chirality centers, if I look at, this CH2 and then this CH2, or all the way around my ring, those all have 2 hydrogens attached to them, so those cannot possibly be chirality centers. What about this carbon right here? Well, I have a methyl group here and I have a hydrogen here, so I have 2 different groups. And it's not quite obvious as I look at a ring system what to do, because I'm supposed to have 4 different substituents. So one way to think about it would be to just go ahead and take this out and make it look like make it look like one of the earlier examples. And from there you can see that there are 2 ethyl groups attached to that carbon. So this carbon does not have 4 different groups attached to it, therefore it is not a chirality center. We can go ahead and put that last carbon back there. And just think about going around the ring now. So if I go around the ring this way, I hit a CH2 group, a CH2 group, a CH2 group. If I go around the ring this way, I hit a CH2 group, CH2 group, CH2 group. The paths around the ring are the exact same. Therefore, I do not have 4 different groups attached to my carbon. Therefore, that carbon is not a chirality center. What would happen if I did something like put a double bond into my ring system? So I have a methyl group here and I have a hydrogen. Well, once again, I'm focused in on this carbon. Is this carbon right here a chirality center? Well, I have a methyl group, a hydrogen, so I have 2 different things attached to it. It's sp3 hybridized. What about the paths around the ring? Well, if I go around the ring this way, I would hit a CH2 and then a CH. If I go around the ring this way, I would hit a CH2 and then a CH2. So I have different paths around the ring. Therefore, I have 4 different groups attached to my sp3 hybridized carbon. Therefore, this is a chirality center. So think about the paths around the ring when you're trying to assign chirality to ring systems.